Lecture 25. We conclude our discussion on submodular information functions. Look at submodular function maximization and the submodular library and its applications. So very briefly, we talked about the submodular information functions, and here are some properties that we flashed in the last class. So recall what is a polymetric function. And the best way to remember polymetric function is matrix rank, right? What are the properties of matrix rank function? F of empty set is empty set of columns is 0. F is monotone, right? F is submonotone. Right? When we talk about the argument is basically what? It's a set of columns. Okay. So now if it's a polymetric function, then there are some properties I want to know as homework, given this as homework actually. It's non-negative. But not only it's non-negative, function conditioned on B, A conditioned on B is non-negative. The mutual information is non-negative. Conditional mutual information is also non-negative. So just make a note. We won't go back into the definitions. Right? That's we have been doing for a while. Monotonicity is not for mutual information, but its monotonicity is for the first argument of F and also the conditional gain. Likewise, monotonicity is for IFAB if you have B fixed. Then it's a function of A. You can't have it as monotone for both. So just taking this ahead, if you have B and C fixed, then it's monotone in A. Or if you have A and C fixed, it's monotone in B. Also, the conditioning as it increases in size in some sense. So the function value reduces. We always thought of f of A as f of A conditioned on the empty set. But then there's a lower bound of 0 because we already seen it's non-negative. This property. And f of A intersection B is a lower bound for the mutual information between A and B. We always visualize mutual information as the information of the intersection. But here we see that the function value on the intersection is still less than the mutual information because it's not the intersection, it's through the function that we see the mutual information, right? So that's slight difference. We saw in the case of set cover. So you could have two disjoint sets which have overlapping coverage. And this is less than or equal to the min of the two function values. And yeah, so on. I mean, the last inequality kind of is a generalization of the second last inequality. Okay. Now, f of A given B, f of A and f of A given B are both submodular, but f of A given B is neither submodular nor supermodular in B. So we can't make either assertion for B. Then we moved on to partial derivatives, right? So that that brings us to the next set of slides. But we said that submodularity of the mutual information depends on some higher order derivatives. In this specific case, third order partial derivatives being known. Okay, so that I think that I missed this slide. So how is it related? So monotonicity requires that the first order partial derivatives are non-negative. Some modularity is about the second order. Okay. So monotonicity is about first order. Submodularity is about second order partial derivatives being non-positive. And that should ring a bell in your mind because we always related submodularity to concavity and convexity. But here it is non-positive, so it's concavity, right? Concave functions have second kind of non-negative, so non-positive, second order partial derivatives. Non-positive or non-positive second order partial derivatives or non-positive definite Hessian. This is that's how we write it, right? Definitely. So you could also now talk of third order partial derivatives, which is important for mutual information. That's what I mentioned. Third order partial derivatives to be non-negative. And what does that mean? It means that here in second order, I was looking at I, right? The gain in terms of I when you have an additional element j in the conditioning set. Here you're talking about adding two elements at a time. In the case of third order partial derivatives, I and j, right? In the presence of k as against without the presence of k. So, I mean, you could draw some connection with, say, Lipschitz smoothness if you want. Right? Yeah, but I won't do that formally. But it turns out that this the non-negativity of the third order partial derivatives, this is satisfied by set cover, facility location, concave over modular, power law function. So that which would imply that these functions should have submodular mutual information as well. Yeah, but then simple uniform rank functions, metroid rank is an example of polymetroid. That does not satisfy this. They may not be cardinality of a comma k. Okay, so this is this is our case of third order partial derivatives. Now let's look at applications. So if you are looking at something like query relevance, so if I give a query, and in response to that, I want to measure how good the set is. Right? So that query relevance can be viewed as a problem of, or retrieving query relevant documents. It can be viewed as a problem of maximizing mutual information. Right? I think of this as a measure. So if you want to retrieve this, you could measure the mutual information I of the set A. Let's say let's call it A, comma Q, where this is the, let's say, a query Q being passed. Likewise, for privacy preserving, I could have a P, and I might again, I might be interested in, so my personal information not being revealed, my face information not being revealed. So to retrieve, what would we measure? Oh, to measure something like the conditional gain of A given B. This is A. Something is wrong with this screen. No, for those on the call, just wait a second. It's a problem. Project. Okay. You could also have combinations of these. Could have query and privacy preserving both, right? So basically, what we have now provided is a unified framework for extractive query and privacy preserving summarization. So you could have, a combination of coverage, representation, and diversity. And this is query agnostic, right? You could say maximize the set with respect to x subset of v, f of x. But in the query sensitive or retrieval setting, you would say max x subset of v, f of x, rather I f of the same f, x comma q. The privacy preserving case, you would say max x subset of v. I use f directly, but f of x condition on or any of these, right? Any combinations. That's exactly what I showed. Now I could further put a cardinality constraint. Cardinality is important, especially if the function is monotone. If the function is not monotone, I might still go away with that without a cardinality constraint. Right? So cardinality constraints are absolutely unavoidable. When f is monotone. Otherwise, you keep doing the set, the function value will be happy. So there's no limit. So we'll see a little bit more of this today because we'll be talking about optimization algorithms. Yes, please go. Sorry? What privacy can do? So if imagine that I have my face information, or I want to search for cars without people because I don't want to reveal people identity who are driving cars. So I might say X could your V could be set of all images. And P could be people faces. Right. So what would be the retrieved X? X would be images without people. And as a result of maximizing F X given P. Is that clear? I'll show more examples. So you could have a combination. I can say I don't want to avoid people images. Right? But I might say that I'm interested in nighttime images. Right? So therefore, I'm looking at summaries which are nighttime images without people. I'll show more examples. So yeah, these are the extreme cases. When Q is V, it's basically f of x given P. So Q is redundant, right? So Q being the entire set, V is vacuous, redundant. Right, and therefore it just vanishes. Right? Its effect is not there. Likewise, if you have the privacy set as empty, then you would have again redundant information. Instead of saying sensitivity to people, I say sensitivity to nothing. I just get the same old summary. And that's also reflected here. Okay, so this is what gives you a unified optimization formulation with these extreme cases being special cases. So if f is a polymetric function, satisfies the property that triple partial derivatives are non-negative, then this is by by virtue of all the results so far, then if a comma o, so this is q, qp is monotone submodular in A for fixed Q and P. Okay, so this is all fine, but now we are coming to the next part. What is the implication of all this with respect to algorithms? Well, it turns out that a greedy algorithm for submodular maximization will achieve this 1 minus 1 over E approximation. In fact, you'll see this and more. Okay. Having motivated, sufficiently motivated so many different classes of functions. Now let's see how algorithms can be effective for this. Okay, so this is just to kind of give you this idea again. So you can do subset selection based on representation, diversity, and coverage. And you can do query focus summarization. I give this example. This is an image set B. You can say query is person, then I'll get only people. But if privacy is person, so these are two different sets. If you have query is person, then this is X, which is argmax or xq, argmax over X subset of B. X cardinality less than or equal to k, or in this case 2 of I f x comma q. On the other hand, what is this? This is again of size 2. This is xp, which is argmax over the X subset of B with cardinality of X set to less than or equal to 2 of the conditional gain of X given. Right? Is this completely clear? It's not summarization. So now if your f is a representation function, then it's trying to represent all the images well through facility location, right? If it's diversity, then I'm not trying to represent. I may even get outliers, as you've seen before, right? Diversity may give you outliers like this, but in a way that is sensitive to the query Q, or maybe agnostic to P. Right? Coverage will look at how concepts are being covered rather than images being covered. Yeah, please ask questions. Yes, it's a good point. So here, for example, you see a woman. That's in the spirit of summarization. It's not just got two men. It's got a woman, like long hair, and a man. Whereas in the second summary, you will find there are two different colored cars, right? Car 1, which is red and maybe long. I mean, it's got a side view, but this is, or I should say, side view. And this is a black car and front view. So it has certainly got diversity. I mean, it's got the summary. Right. So this is our basically. Welcome to read this paper called Prism 2022 AAA. Forgot to mention this. I'll bring this up again later on, but there we give use cases. In addition to this query, here's another use case. So imagine that I had a queue which is nighttime images. Okay. That's what we call the target. And then I have my V, which is a lot of unlabeled data. So what will I do? I'll take my unlabeled data V, look at Q, and do targeted subset selection. How is targeted subset selection going to operate? It's going to say, well, I'll say my T is argmax. This is my T, argmax over X subset of V. If you want to put a cardinality constraint, if you're monotone, especially, you must. Of what? Of the information function, some information function at IF of T, comma, or X, comma, Q. This is my target subset. Now identify the target subset and I label it. Why? Because this looks like nighttime images. And it's a subset of the unlabeled data, which is worth labeling because it's aligned with my target. Is that clear? This may be about, and then you can keep doing this. In fact, you can keep the loop on. Augment with, create more labeled data, retrain your model. This is not clear. Not this. We'll talk about scaling. Right, so this is this part of submodular library, but specifically we have a library called Trust within Decile, where this is implemented. Okay, so decile.org. So we have chords, we have distill, but there's something called Trust. So yeah, Trust is part of it. Okay, but many of these functionalities are in submodular bits. So I'll focus more on submodular. Okay, so here's submodular. And we'll be going over the algorithms here. So it has a rich suite of functions, regular set, submodular, mutual information, all that. But now what I'll move to is different optimizers it supports. So from optimization perspective, is submodularity like convexity or concavity? It turns out it has properties of both. What we'll focus on more is this concavity properties in terms of maximization. So convex, the convex aspects, which is about duality, efficient minimization, right? Which I'll not talk about much because this convex extension, the usage is maybe relatively less in machine learning. A lot of usage otherwise. So you can actually come up with this kind of Loa's, it's called Loa's extension. Actually, other extensions as well, which is a convex function, convex kind of relaxation. And they're very efficient solvers for submodular minimization. However, from a concavity perspective, we have always found that submodularity behaves very much like concave functions because of this diminishing returns. So this is what we have seen, right? Now it turns out that there's something even stronger in terms of connection with concavity. I had promised this will come up later. Now it has come up. The fact is, if FA is submodular, where FA is defined as G, a function G on the cardinality of A, then it must be that G is concave. And if G is concave, then it must be that FA is submodular. So a function F defined to be a function G on the cardinality of A is submodular if and only if the function G is on the cardinality submodular. Okay. We've seen an example. I mean, we've seen square root earlier, right? Square root. Then, for example, square root of cardinality of A is submodular. But it's an if and only condition, both ways. Okay, so the concave aspects are interesting from maximization perspective, as you would expect. Convex for minimization. However, for convex aspects, solvers are more efficient. Efficient polynomial time solvers. For example, if you're trying to do map estimation on graphical models, right? Under simple submodularity conditions, there are well-known polynomial time algorithms. So let's say you have a grid. Okay, so and you're trying to find, say, image segmentation. For image segmentation, you remember the submodular property that if you're trying to do energy minimization, the energy of 0, 0 plus 1, 1 should be less than the energy of 0, 1 and 1, 0. Sorry, other way. No, 0, 0, 1, 1 will be less than 1, 0. So for image segmentation with submodular function, there are polynomial time efficient algorithms, and that's because by virtue of a minimization formulation. Okay, but these are mostly inference, less of learning. They are very useful in inference. They also can be useful for feature composition, feature induction. Okay, so Francis Bach, and I've also done work in the past. If you're interested, we can point you to that. But we want to focus more on maximization now. For maximization, unfortunately, many of the problems are NP hard. Generally, the problems are NP hard. However, there are very, there are greedy algorithms which are very effective in practice and often have good approximation guarantees. I'll talk about what that means. So that's one reason we are able to do something useful with also concave. I mean, actually lots of useful problems we can solve, but because the algorithms are efficient, they're not bottleneck. And the algorithms are not only effective in practice, they also have some good approximation guarantees. This is like a summary. Convex aspects on the left-hand side, minimization has polynomial time algorithms. There are convex continuous extensions like Loa's extension. Notions of subgradients and subdifferentials. You remember this, right? Those are pretty evolved. There's also notion of convex duality, discrete separation, and so on. Whereas for concave, constant factor approximation algorithms for maximization, there are also extensions which are multilinear in a direction. Instead of subgradients, you can now talk of supergradients. This is an example of a supergradient. It's subtending from the top. And under certain restricted settings, you can also talk of duality. We'll talk a little bit of, we'll allude to, Lagrange multipliers here. Remember, we use a Lagrange function, right? That will be certainly today. We'll do that today. Okay, this is a bird's eye view. So let's now plunge into the maximization of submodular functions, which are very useful in machine learning. So what's the more general problem? You have function f, which could be diversity, representation, coverage, right? Applied on subsets A of the ground set B. F could be monotone, it may not be monotone. It could also be sometimes related to submodular functions, but not exactly submodular. We've seen dispersion functions, right? We've seen min sum, for example. Now, since the function can be monotone, it's often important to have a cardinality constraint, or more generally, a selection cost. So C is a cost of selecting a subset B. And you want to make sure that that doesn't exceed your budget B. So this is the master optimization. Any questions on this? Okay. So f of A, for example, could be submodular utility. C could be a supermodular cost function. You could also have combinations, right? So you could have UA minus EA. So in general, the problem is NP hard. And we can show that a specific example of F is set cover. So you can show that this kind of cardinality constraint set cover problem, the very specific case is itself NP hard. So obviously the general problem is NP hard. NP hard to, in fact, is as hard as approximate, as hard to approximate as maximum independent set problem. Okay, but despite this, there have been efforts for exact maximization. Now you could do the following: you could actually be ambitious and have a mixed integer program, a series of mixed integer programming, for example, as early as 1981, Nemhauser tried that. We'll show some other results from Nemhauser today. which are not about exact maximization. So there have been other works on using constraint generation, branch and bound. So you basically at every point, at every step, you find an upper bound. So obviously these are useful, but then they are exponential in the worst case. So therefore, they are really not practical. These are not practical for operational ML settings. So what we'll do instead is, we'll consider simpler functions and see if there are interesting algorithms and interesting approximation guarantees. So we'll start with monotone submodular functions. Monotone would mean that you need a cardinality constraint. Otherwise, the function can keep growing. Right? So, for example, you can see that the cost function here is just the size of the S. Could have also other cost functions. We'll look at other cost functions soon. Okay, so the greedy algorithm, the simplest of the lot, is as follows. You say E star is argmax of all the elements E which are not in the currently populated set Si. You begin with S0. Then what you do is S1, you identify for S1, you identify E star is all the elements across all the elements E in the set V minus S0, which is the set V of just F on E, because the current set is empty. Right. So then what you'll do is you'll have S1 equals S0 union E star. And then now you'll consider the next E star, E double star, whatever. So that will be argmax over E in V minus the previous E star. So you can say minus S0, which is, S1, which is just one element subtracted. But now you look at F of E, the previous E star. Okay, so, or you want to call it E double star here. So E star union E. This is a simple greedy algorithm. This is how you loop around. Keep doing this. Before that, after that, you do S2 is S1 union E double star. So how good is this kind of SK? SK is the set after cardinality K is reached, right? So SK is such that size of SK is equal to K. So it's monotone, and obviously function cannot decrease. It's possible that some element doesn't lead to any increase at all. That's possible. So the cardinality may be less than K. It's possible. Right? How good is this in practice? Okay, anyone has tried using? Have you evaluated the goodness? Okay, so it turns out that if you're trying to do sensor placement, you can see these are sensors, nodes, and each sensor has some area of coverage. Look at the information gain, basically the gain by adding each sensor. In an optimal setting, optimal is some oracle or some brute force gives you the optimal set. Okay, and then you basically look at that as a function of the number of sensors placed. You'll find that the greedy algorithm is not too far from the optimal. Of course, as the number of sensors placed increase, the gap can be expected to widen, but it's sometimes within 90%, 95% of the accurate, the optimal solution. So, how good is greedy in practice? Greedy can be very good in practice. But there's more to it. In theory also, greedy can be very good. And we're going to do this proof a little carefully. So it turns out that the function applied on the set obtained after k steps sk is at least as good as 1 minus 1 over e into the function on the optimal set S star. What is 1 minus 1 over e? Roughly 0.63, right? So that's pretty good. 0.63 times the f on the optimal is the lower bound on the function at sk obtained using greedy for a monotone submodular function. In fact, no polynomial time algorithm can do better than this in the worst case. That's also been proven. Worst case of the f, for some pathological f, you'll land up getting this. So you remember the worst case is always done by construction, and we did that, right? For you remember the Lipschitz continuity, smoothness, combinations, right? And these by adversarial itself. This was gradient descent. It was not just gradient descent, gradient and variance. Right? We saw that earlier. Okay, so that probably explains one part why this is a very reasonable lower bound. So let's try and prove this. I'm going to get started, and then you can probably note down some important steps. So we are going to have AI as the chain formed by the greedy algorithm, which means that I began with A0, then I added an element V1, sorry, to get A1, which is V1. Then I added V2, find V1 and V2 as a new set till I reached V1 to here. So this is a chain. Order in this is important. But we also have an A star which has V1 star, V2 star, VK star. Obviously, it's monotone, so we'll assume that all the K budget was exhausted in constructing your A star. But the ordering won't matter. Okay, so in an arbitrary order. So here the ordering doesn't matter in A star. In A1, AI, the ordering matters. That's how you're constructed. So opt of F A star is the value of the optimal solution. Okay. A very important key step I'm going to outline here. So f of ak. Now there are multiple ways you can write f of ak. One thing we're going to see is that you can write f of ak as a telescopic sum from a star to ak. Can you think of how you would write it? That's going to be key. Okay, key step in our proof. Many of the rest will just follow, but this might require a little bit of thinking on your end. Okay. So can I write this as a chain of differences? Such that in subsequent terms that some of the terms of differences get cancelled with the previous ones. So can I write this as, sorry, v given ai minus 1, which v? So let's say vk given ak minus 1. So what is that? Vk given ak minus 1 is vk union ak minus 1 minus k. And then summation, okay, summation I. I is equal to 1. Is this correct? Let me just expand this, right? So this is vk union v1 to vk minus 1 minus f of, if f of v1 to vk minus 1, right? So this is any term here, if you want, then expand. F of v1 to vk minus f of v1 to vk minus 1 plus f of v1 to vk minus 1 minus f of v1 to vk minus 2, right? So many of these terms will get cancelled out. So this will get cancelled out like this, right? So what will remain at the end? There will still be some f of minus f of, so a0 is empty. F of v1 minus f of f of 5 will remain, right? So that will remain f of 5. Now, did we assume f of 5 to be 0? F of 5 is 0, then you have polymetroid. Now, is f of 5 required to be 0 here? Let's come to that. Okay. Now, f is greater than or equal to 0. But we didn't assume that f of 5 is empty. Is that required? So we'll see that we'll see that next. But the key step is this telescopic sum, followed by application of monotonicity and submodular. Okay. These are the key steps. Just call it steps. This is the first step we are shown here is telescopic sum. Okay. So now I'm going to do slightly differently. So I'm going to use telescopic summing, but I'm going to use telescopic summing not on AI. Just wait for me. I want an inequality. So f of a star is less than equal to f of a star union AI for all I less than equal to k. And we'll write the reason. Why is this true? For all I, why would this inequality hold? Let's give reason here. This is because it's monotone. So to a star, I just add any AI, it cannot decrease. The second step I've done is telescopic summing. So this is what we're going to look at really carefully. But only thing is, I have applied telescopic summing from previous side. Applied to what? Applied to what? F of A star union A. That's it. I change the argument. Okay. So if you want, we can use delta. Delta is basically gain. So if you want, call it delta, call it F. This is conditional gain. So delta, let me just write this. Let's write the summation. J equals 1 to K. Okay, I change the indices also. So let's write this. J equals 1 to K of delta of Bj star given AI. So what is this summation? Let's write this. So this is nothing but f of Bj star of Bj star union AI union V1 star to Bj minus 1 star minus f of the same thing, but Vj star without Vj star, right? AI union V1 star all the way to Vj minus 1 star. Correct? And then the next term. So now you can see it's the same thing basically unfolding. Plus the same term. Minus. So now you'll keep doing this. You'll have the same term coming up again and again in plus and minus. Except for the last term, which will be what? Huh? AI, right? Because J equals 1 to K. By the time I've added all the K, sorry, what did I do? I shouldn't have used K. I should have used K. Sorry. I should have used K here, right? J should have been just K. Is correct? K. And finally, K will be equal to J will be equal to 1. Right? And J equals 1, what will we have? What will we have? We'll have this, f of A. So the first term will be B1 star minus f of AI. So just go on minus f of AI. And therefore, if you bring this minus of f of AI to the left hand side, you can get f of AI here. So just in summary, this term plus this green term brought to the left hand side is f of a star. Let's see. Oh, I forgot. Yeah, a star is a star union. This is one. First term. Okay, so this I should point out. This term is nothing but f of a star union. Is this clear? F of a star union ai is exactly this term. F of ai union e1 to ek. Stop. The gray, the green, and the yellow tones. Remove the minus from there. The minus I had marked in green, which is undesirable. This F of ai. Is this clear? So this step is a telescopic summing. That's it. That's why in the previous slide I took a simpler telescopic summing on AI. Now you can apply it to AI union case. Okay, so this is why the question is, why are we unioning AI with A star? Well, it's part of the proof methodology. That's it. So you just bear with it, because there are a bunch of inequalities coming up after this, where all that will vanish, right? So left hand side is something we are comfortable with, A star, right? So right hand side we want to get into something we are comfortable with. A good question. So we have f of A star on the left hand side, and we want to see how we can simplify the right hand side. Okay, so after that, the green part will remain throughout. Okay? There's going to be no change in this f of ai. That will remain. What we'll do is, which you are comfortable with, right? It's exactly what you like, right? That the gray part you don't like, and we'll do away with the gray part. We brought in some overhead and get for the proof methodology. So what is happening here is Vj star. What is Vj star given ai? It's just Vj star is an element added, right? But Vj star is just some element of A star. There was no ordering between the elements of A star. Okay, so note. Please ask questions if you have. Huh? I mean, I don't mind going slow on this. Note that each Vj star was just some element of A star. There was no real ordering between the elements of A star. So therefore, what I do is, instead of bothering ourselves with the index on the J star, we'll do away with the index. So I'll just call it Z. So it's just any Z in A star. Why should I give it a particular name Vj? Or why should I persist with the name? I give it a name for telescopic summing, but other than that, Vj star is just some Z. So that's what we have done here. In the expression below, we just call it Z in A star. And any such Z in A, so if you want, you can continue, right? So if you want, you can say, actually, let me just Right? So the summation delta Vj star, delta is the same as gain, right? Of AI, it's the same. I'm just expanding this. AI union P1 star to Pj minus 1 star. I'm saying this is, this was for J equals 1 to K. And you're saying that, well, A star itself was just as V1 star to K star. Now, this V star could be abstracted into Z. So if you want, you can write this as, we'll do that abstraction. But the other point I want to make is this Vj star, when added to a larger set of AI, a superset of AI, is going to give you less gain or not more gain than when added to AI itself, right? So this inequality should hold. So this inequality holds. Why? Because even without the summation, the inequality holds. Right? So since this holds by submodularity. Is this clear? That's what I was trying to show here. This using submodularity, when we say this holds by submodularity. I'm just making a note here. C. But not only that, now I have also abstracted the name to Z. So I've said, okay, this is the same. I mean, whether I call it Vj star or just Z doesn't matter, right? So I'll just say Z in A star of delta Z given A. This step. So just let's give it name if you want. Let's call it this is step 2. Step 2 is clear. Next slide. Next slide. Which slide should go? In A star, there may be some B's which are not in AIs. It cannot be smaller. See, the point is this AI union VI to VJ star cannot be smaller than AI. It may turn out to be the same as AI. So as and you want, let's be very specific, AI union P1 star to Pj minus 1 star is a superset of AI or cannot be a subset of it. Is the step 2 clear now? Please ask questions. This is good that you're asking so many questions. Okay, so the step 3 is what? So in step 3, we are saying that, well, Z, when it's getting added to AI, cannot be better than Vi plus 1 when it got added to AI. And that reason is very simple. We are saying that you have added Vi, Vi plus 1 itself was considered because it was argmax over all the elements which were not in AI of the delta of V given AI. So this is very, so let me, step 3, let me elaborate here. So since Vi plus 1 is argmax for all the elements in the current in V which are not in AI of V. So when I was at AI, I tried to find the next element which gives you the maximum gain by virtue of the greedy algorithm itself, right? So therefore, what I can say is the delta Vi plus 1 given AI cannot be less than the delta Z given AI for any Z in 1. So it should not be in AI. Any Z in. So let's look at this inequality again, right? So you want to make sure that this Z is only with respect to those points which are not in AI. Z in A star. How do you assure that? Maybe somebody can argue that the set. See, can Z be a part of AI? Can Z as part of AI give you better gain than some Z not in AI? So let me write this down, right? So I'm making this claim. For any Z in A star, this holds. Why? Because this holds for any Z in A star minus AI also. So this was for any B in B minus AI, and A star is a subset of B. A star is not greater than B, right? It's a subset of B. It's not outside B. Okay, so it's a small observation. It's basically this is the main thing. Vi plus 1 is that from B minus AI that maximizes delta V given AI. And this includes all the Z's in A star minus AI. Is that clear? But obviously, Vi plus 1 cannot be part of Vi. Oh, sorry, AI. Okay, so this is straightforward. This part we have no problem at all by design. Now you add this for all the Z's and A stars. So say delta Vi plus 1 given AI. But now the summation on Z has become redundant here, right? In this step. The summation on yeah, I can write this here. Summation with respect to Z has become redundant. So therefore, you'll have K times delta Vi plus 1 given here. That's it. So now after this, we just rearrange the terms. We have just take the delta to the right hand side. So we have after all of these steps f of A star being less than equal to f of AI plus K times delta of Vi plus 1 given AI. And now you just rearrange it further. Delta of Vi plus 1 given AI. Just move it this term is greater than or equal to 1 upon k times f of a star, which is the same as opt. Is the same as opt. Minus f of ai, the whole divided by 1 upon. Is this okay? Okay. So now we are pretty much there. Now just a little bit more left. So again, I have those relations. Opt is f of a star. Now I'm going to look at the delta I, the difference between the f of a star and f of ai subsequently, right? I mean, as I keep growing ai. So if delta I is opt minus f of ai, then delta I minus delta I plus 1 is just f of ai plus 1 minus f of ai. So the order will change because it's a negative. Delta I minus delta I plus 1 is f of ai plus 1 minus f of ai. This is exactly the same as, now I'll just color code. Delta I minus delta I plus 1 is the same as delta vi plus 1 given here. The conditional gain of adding vi plus 1 to ai. This, so what we have from the previous slide, right, where we said delta vi plus 1 given ai is greater than or equal to 1 upon k, right? So let me just bring that up again. Okay, so I'm just recalling the right, with again the understanding that this term on the right hand side was exactly delta I minus delta I plus 1. So delta I minus delta I plus 1 is therefore greater than or equal to 1 upon k. Opt minus f of ai is delta I. So we just plugged in all these different terms from above. This is clear. So now I just want to write the expression in terms of delta i's, the gap of the function on ai from the opt. That's it. So delta I plus 1 therefore is you can bring the delta I to this side, 1 minus 1 upon k delta I. Now you can see where the e is coming from, 1 minus 1 over e, right? This should be very exciting to everyone. This inequality is the key here. Delta I plus 1 is less than or equal to 1 minus 1 over k delta I. Now I can apply this, right? I can apply this recursively. That gives me delta k is less than or equal to 1 minus 1 over k, 1 upon k raised the whole raised to k. Apply this again and again, right? And what is how often how long does this go? Well, it goes as long as delta 0, right? And what is delta 0? Delta 0 is opt minus f of a0. Okay, so so can I say that this is less than or equal to opt minus f of a0? Is that less than or equal to opt? Okay, so that's it. So this is data. We didn't need f of a0 to be set to 0. Right? This the whole thing is is less than equal to opt. That's it. So now limit as k tends to infinity. I mean, as k, you can keep, let it go large, right? What will that be? One minus one over k, the whole raised to k, it will tend to 1 upon e, right? And in fact, this is an this is a strict inequality. This is an inequality, not strict inequality. This 1 minus 1 upon k, the whole raised to k is less than equal to 1 upon e. So that's how we get this. Okay, so I think the rest is simple. A delta k is again substituted to be opt minus f of ak. This gives us the final result. F of ak, the function evaluated at the k steps of greedy, will be at least 1 minus 1 over e times the opt. This is okay. Any questions? Okay. Okay, so this is monotone submodular function with greedy algorithm giving you at least 1 minus 1 over e at 0.63 times the opt. But what if you have some other constraints, budget constraints, not cardinality constraints, right? So generalizing beyond cardinality constraints. So now I'm going to go do proofs. I think the intuition of one very elegant proof you have got. Okay, the proof was completed. So what happens if you have, say, cost, CE, associated with each element? Well, you might say, let me have a modified greedy. E star is argmax over all the elements E that I could add to SI. Right? But the marginal gain divided by the cost. So it's like gain per cost or conditional gain per cost. Let me just give it a name. This is like conditional gain per unit cost. Right? So I'm not looking at just conditional gain alone. Okay, so Swiridenko in 2004 said, you can do this, but do the following. Before you run this, you need to do a little bit more work. Okay, so this is the cost sensitive greedy algorithm. But you start with all possible initial sets, LJK. Okay, don't basically decide on one particular set. So it's effectively saying that, okay, initially you do a kind of brute force search on all triplets. So you're basically doing this is the initialization part. With all possible initial sets LJK, that leads to order n cube complexity. So effectively what we are saying is initially do find the best triplet, E1, E2, E3 through brute force search. If you did this and then resorted to a modified greedy, you get a 1 minus 1 over E approximation again. Okay. This is when you have budget constraint. But obviously, you're not very happy with this, right? Why? Because order n cube. I mean, what was the complexity of greedy? By the way, I didn't make that explicit. What's the complexity of greedy? There's a greedy element. Complexity is what? N square. So what do you do at every time step? you scan all the n, right? So, but you do this for how many times? Right, right. So you'll have n plus n minus 1. N minus k, right? N minus k plus 1 2. So roughly you're looking at n into p, right? Looking at order n. But let's look at this, right? So this is order nk, but after an initial order n cube, which is too much. Can you do better? So the same idea. What this is the follow-up work from Leskovec. Okay, Leskovec said, let's add an additional step. So instead of doing this, we were canceling this out. Let me just cancel this. Instead of doing this, what Leskovec says, the core algorithm of modified greedy you use, but you also run the normal greedy, right? So it's possible that it's not worth taking the gain, the conditional gain per unit cost. Just go for normal gain. So ultimately, what you're going to do is look at normal gain, right? The per unit cost is coming only because you have a cost constraint. But why put it in the constraint? Try running normal greedy, run a normal modified greedy, and pick the better of the two. So that's been avoided here, right? So the question being asked is, why not do this NQ instead of NQ for the first three to greedy? I mean, yeah, see, you can do it. Practice, you can do many things, but then what is the approximation guarantee you get? So, in fact, I will tell you, I mean, simple greedy also works pretty well, right? But the issue is approximation guarantee you can get using some of these tricks. So, if you, I mean, there have been some recent work which have tried to bring down this order n cube to order n square as well. But still, order n square might be prohibitive. And this complexity is still just what is it? It's order nk only, right? And the approximation factor. This still gives you an approximation factor of not a 1 minus 1 over e, but half. Now this is not very satisfying, right? So this is basically now you've got to 0.365 or something. You are not happy with it. Okay, so but in practice, as I said, even this works well. So this is the overall summary of the greedy algorithm framework. You have a monotone submodular function, and you can do greedy selection, or you can do a cost normalized greedy selection till you reach the budget. Okay. I want you to give some thought to this. I'll talk about it. This is going to be a homework problem. And what is the homework about? So this is a dual problem. What is a dual problem here? So, in fact, I would encourage as a homework to try and code it up. It's a simple idea. And I'll tell you, we have tried this out. So the dual problem is that I put the submodular function in my constraint. Oh, I put the submodular coverage, for example, like minimum coverage. I don't want coverage less than some q, right? But find the largest, smallest set that satisfies my coverage constraint. Okay, it turns out the same greedy algorithm. What I want to do is, as a homework, just try implementing for the same problem, try both, okay, and see what works better. I'll tell you, surprisingly, both, I mean, the approximation guarantees are different, but in practice, they give similar results. I'll write down the homework problem immediately. Thanks then. Yeah, bye.